There are three kinds of braking used in a SureServo2 system. Dynamic braking, which is used to stop the motor quickly when you disable the motor, issue an override, or have a fault. Regen braking, which is used while the motor is running to create super fast deceleration ramps using a regen resistor. And electromechanical braking, which is used while the motor is stopped to keep it from spinning. This video covers regen braking. Most of the time, we want to control the deceleration ramp. The problem is, when you try to slow a motor down faster than it would normally spin down by itself, the motor becomes a generator and pushes current back into the drive. That charges the capacitors, which raises the internal bus voltage, and if that voltage gets too high, it can damage the internal components. Now the drive won't let that happen, of course. It'll fault out and shut down before anything bad happens. But we don't want our system to fault out, so how do we avoid that? Well, the SureServo2 drive monitors the bus voltage, and when it starts to get too high, it automatically reroutes the excess energy to a large wattage resistor where the energy gets burned up as heat. If you're familiar with VFDs, you'll probably look at that and say, oh, that's dynamic braking. Yeah, I agree. But the SureServo2 uses the term dynamic braking for a different braking method, where the drive dynamically adjusts the deceleration ramp to prevent the bus voltage from getting too high. So we'll refer to this braking method as regen braking. In dynamic braking, the drive controls the decel ramp. In regen braking, you do. The cool thing about the SureServo2 system is regen braking is built in and enabled by default. And drives through 3 kilowatts even have the braking resistor built in. So since I'm using a 400-watt drive, we don't have to do anything to set this up. Do you have to use the built-in resistor? Nope. You can disable it and use your own external resistor if you want to. We'll cover how to do that and why you might want to later in this video. I'm using the same hardware as we used in the quick start video, except I added a 4-pound pulley to give us some inertia. I reset the drive to factory default so you know exactly where I'm starting from, and power cycle the drive. That clears out any residual non-volatile memory locations. I then changed it to the speed mode that guarantees the first speed is absolute 0. And power cycle the drive again. That power cycle is real important because it sets up the drive for the new mode. And here's a tip. If you can't get the motor to spin after a mode change, it's probably because you forgot to do that power cycle. In speed mode, you can set up 2 digital inputs to select one of 4 preset speeds. I'm using digital inputs 9 and 10 for that, and since we're using speed mode 4, this is guaranteed to be a 0. These are the default speeds for the other 3, but I changed this one to 3000 RPM so I could just toggle this one bit to quickly switch between 0 and 3000 RPM. These are the parameters you need to do all of that, and I set the speed mode decel ramp to 1 millisecond, which tells the drive to decel as fast as it can. So we have a 50-to-1 mismatch on our load and the fastest possible decel ramp. Yeah, that's asking a lot of the drive. I also tuned the drive to this load. Check out the auto-tune video to learn how to do that. Okay, let's bring up the SureServo2 Pro software scope function. I have the commanded speed in white using 32 bits, so it uses 2 of these. The actual motor speed in purple, also 32 bits, the bus voltage in red, and the motor current in yellow. Let's get the scope running. I'll enable the servo motor and flip this switch to tell the drive to go to 3000 RPM. The motor ramps up to speed. I'll turn the speed switch back off, and sure enough, the drive ramps quickly down to 0 RPM without a fault. Perfect. I'll stop the scope and zoom in. Look at that. It took the drive only around 160 milliseconds to bring that heavy load to a nice, clean, full stop. That's amazing. We see the current going back into the drive was a strong 8.5 amps, and the bus voltage rose from 170 volts to almost 320 volts. Keep in mind, I'm using a 120 volt drive here. If you're using a 220 volt drive, then your nominal bus voltage will be around 312 volts, and it'll rise proportionally due to regen. Okay, so out of morbid curiosity, what happens if we don't use a regen resistor? The drive has some capacity to absorb energy. Will it have enough? Let's find out. I removed this connector, which has this jumper pre-installed, which connects the built-in regen resistor to the drive's braking circuit so the current flows through the resistor. With the connector removed, this is gone, so the drive has no regen resistor to dump the extra energy to. Let's see what happens. I'll restart the scope, switch to 3000 RPM, and then back to 0 RPM. Well, that's interesting. It looks like the drive handled this massive load just fine without a regen resistor. Or did it? Look, we got a fault that tells us something's wrong with the regen circuit. And if we zoom in on the decel ramp, we see something interesting. We got our expected linear deceleration ramp until here, but when the bus voltage rose to around 240 volts, the ramp took on a different trajectory and the current consumption backed way off. What's going on? Well, this is the drive handling the regen energy on its own without a resistor attached. But when the bus voltage got too big for it to handle without the regen resistor, the drive switched over to the dynamic braking method, which dynamically manages the decel ramp to reduce the regen current, which allows the bus voltage to relax. Now I say relax, but look, the bus voltage got up to over 400 volts. We can prove that's the dynamic braking taking over by simply turning it off. I'll reset the alarm, go to parameter 1.032, and disable dynamic braking. Start to scope, ramp up to 3000 RPM, and then switch back to 0 RPM. Look, the drive is free spinning down. I'll fast forward the video so we don't have to wait. I'll stop the scope and adjust the display. Sure enough, the drive tries to consume the regen energy, but when the bus voltage hits around 240 volts, it gave up and passes deceleration off to dynamic braking. We turn dynamic braking off, so the motor just free spins down by itself. I'm going to put the regen jumper back in and run one more trial to make sure everything's back to normal. Yep, looks great. But the bus voltage takes a long time to settle out. Does that mean I have to wait for it to settle before attempting another deceleration? No, not at all. I ran several trials in a row just to show you. As you can see, as soon as the acceleration ramp kicks in, it consumes all of that voltage to get the drive up to speed. Okay, my drive has a regen resistor built in. You can see what the drive expects for a regen resistor to be in parameter 152, which is the resistance in ohms. This drive is 100 ohms, and parameter 1.53, which is the power in watts. We have a 10 watt resistor. How do I know if that's the right value for my application? Or, if I have a drive without an internal resistor, how do I know what size resistor to use? You can figure that out by going to this table in section 2.8 of the user manual. It tells us it takes this much energy to take the motor spindle by itself from 3000 to 0 RPM. We know our load is a 50-to-1 load, so we need 50 more of these to account for that, or a total of 51 of these E0 guys. This chart also tells us that the drive by itself can absorb this much energy. So if we subtract that from the total energy we have to dissipate, then this much energy is left for us to shove into a regen resistor. Suppose your cycle time is 400 milliseconds. Divide the energy by time, and you get this many watts. If you have two deceleration times during that cycle time, one for the trip out, one for the trip back, for example, then you need to multiply the energy required by 2. And that's a good estimate of the minimum wattage your resistor needs to do this over and over continuously. But consider this a starting point, and then add some common sense and testing to see if it works for you. Just know that if you run a system with a lot of braking, this resistor can get hot. And I mean hot to the touch, so beware. Now, if you aren't running a 100% duty cycle, then you could back off on the requirements proportionally. Again, use your judgment here. The internal regen resistor is connected like this. To use an external regen resistor, pull this jumper and put the external resistor here. Now I happen to have a 91 ohm 200 watt resistor laying around. Is it okay to use that? Well, 200 watts is more than enough, and according to this chart in the manual, I'm allowed to use down to 60 ohms. So yeah, 91 ohms is fine. Could you use a combination of resistors to get whatever value you need? Sure. Just make sure the combination meets the minimum resistor ohms and wattage requirements. I'll plug that into the drive and modify parameter 1.52 with a new resistance value and parameter 1.053 with a new wattage, so the drive knows exactly what it has to work with and can plan out that linear ramp accordingly. I'll start the scope, ramp the motor up, and then back down again. Zoom in on the deceleration ramp. Looks like we got basically the same results as before. Almost 9 amps of regen current, bus voltage rose to around 300 volts, and the ramp time is roughly 160 milliseconds, all of which is pretty much what we saw with the built-in resistor. Perfect. One closing thought. Regen braking can create a lot of energy, which gets dissipated as heat. So it's important you have really good heat sinking and a lot of forced air to help cool things down, especially when relying on that internal braking resistor. In fact, even if you have a drive with an internal resistor, you may want to disable that and use an external resistor instead, just so you can mount it away from the drive to provide better cooling and heat sinking. Again, use your judgment and do what's best for your system. Well, that ought to give you a good idea of how regen braking works in a SureServo2 drive when decelerating the motor during normal operations. And remember, having regen braking built into the drive saves you time, footprint in your cabinet, and money. Just one more reason the SureServo2 system is such a great value. Click here to learn more about the SureServo2 drive and to find more videos like this from AutomationDirect.com. Click here to subscribe to our YouTube channel so you get notified when we publish new videos like this, and click here to learn about Automation Direct's free award-winning support options.